If you've ever seen an old calculus book, a lot of times they were called the calculus because at one time it was almost considered two separate things. There was differential calculus and there was integral calculus. So in calculus 1, we spend most of our time with differential calculus, which is taking derivatives and applications related to derivatives. And then in Calc 2, most of your time is spent with integral calculus, which is integration, which is kind of the opposite of what we've done so far. So integration is the process of finding the antiderivative, and that's what we're going to start working on now. So 4.9 and then chapter 5 is deals with the other part of calculus, the integral calculus, which will mainly be covered in calculus 2. But we get started with it and look at some of the techniques in calculus 1. So to see how this works, let's just start off with something like, let's say, suppose f of x equals x squared, or let's say f of x equals x squared minus 7, or even f of x equals x squared plus pi. Then we could say f prime of x equals, so in this case f prime of x is 2x. In this case f prime of x equals 2x. And in this case f prime of x equals 2x. So the derivative is the same in all cases. So what if somebody asked this question? What is the antiderivative of 2x? So not derivative, but antiderivative, like the opposite of a derivative. So if we're asked that question, we could say something like this. In other words, if f prime of x equals 2x, then f of x equals what? So if the derivative of this function, f of x, is 2x, then what is the original function? So we're kind of like going backward. And you can see in this case, here's the derivative, 2x, right? Each one of these cases, we've got this derivative is 2x. And if you look back to the original function, in each case, it's a little bit different. So to answer this, we could say f of x equals x squared plus c. And this is called the general antiderivative of 2x. So general meaning it's this form, and there are actually an infinite amount of these antiderivatives of 2x, just depending on what c is. C could be any constant. So c stands for a constant. So to check, if this is f of x and this is some constant, then f prime of x, if you take the derivative of this, you're going to get 2x, and that's the derivative of the constant goes away, so you just get 2x. So we can check. So when you're going in the reverse process, like when we're finding these antiderivatives, we can always check our answer by taking the derivative of our answer and seeing if we get back. Right? So the derivative of this is just 2x. So this x squared plus c is the general antiderivative of 2x. And we'll see later there'll be cases when we won't want a general one, we'll want a specific one, but we'll need more information at that point. So little note we have to talk about right now is just something that will happen in section 4.9 with the notation. So here's something to keep in mind. So we will have in this section this function f of x, and then we will have the antiderivative. And let me do this a little differently here. Let me get rid of this part. Oops. Let me do this in a different color to make it clear. So we have this function f of x, and then we have the antiderivative of f of x. And to show that it's the antiderivative, what we'll do in this section, what the book will do is they'll use capital f of x plus c. So there's a link here. These are the same letter, but the antiderivative will be a capital. And to see what that means, looking at these two, we can see that looking at these two, it means that if you take capital f of x plus c and you take the derivative of this, you get little f of x. So this is the notation. So if we have f of x, the antiderivative is capital f of x plus c. So it's a general antiderivative, so c could be anything. So to check that, if you have an antiderivative and you want to know if it's right, you would take the derivative of this antiderivative and see if you get back here. So if it's right, the derivative of the antiderivative brings back the original function. And then one thing that I'm just going to write down just so we're clear on what this is. So integration is the process of finding the antiderivative. And what we'll find out is that taking the derivative of a function is very easy. It'd be really difficult for me to come up with a function that you couldn't find the derivative for. But the reverse process is not easy. It's really easy to come up with a function where you can't easily find the antiderivative, or in a lot of cases, there is no antiderivative written in terms of ordinary functions that we have used in Calc 1. But you'll learn more about that in Calc 2. We'll learn a little bit about it in Calc 1, but in Calc 2 you'll see that it's much easier. It's much, much easier to find a derivative than it is to find an antiderivative. But to get started here, I'm just going to mention a couple of things and see if we can come up with a formula. So I'm going to make up some example problems here. So we've already seen if f prime of x equals 2x. So in other words, the derivative of this function, f prime of x is 2x, we have seen that that implies that f of x, the function itself, is x squared plus c. And I'm going to tell you another one. If f prime of x is 3x squared, then f of x is x cubed plus c. And you can check, right? If you're not sure about this, take the derivative of this. This is f of x. What is f prime of x? Well, power rule, 3x squared. Derivative of c is 0, just goes away, so it's 3x squared. So here is our first formula. See if we can come up with this. F prime of x equals x to the n implies that f of x equals, this is the power rule for integration. We have the power rule for taking the derivative. This is the power rule for finding the antiderivative. And it's closely related, but what we have to do is, instead of going down by a power, we go up by a power. And instead of multiplying, we divide. And then we always have this plus c. And this is true as long as, I'm going to say, there's a little caveat here, as long as n is not equal to -1. It can be anything else, but it can't be -1, and you can see why that would be. If n were -1, and then I go -1 plus 1, I get division by 0. So we'll see that we have to, there's a different thing we do in that case. But this is the power rule. This is called the power rule for integration. And it's just, like I said, it's the opposite of the power rule for differentiation, where if we have, like, let's say we have f of x equals 2x to the fifth, we would go f prime of x equals, and the 5 would come down. Actually, you know what, let me make it a little simpler just so keep it simpler here. So the power rule says the 5 comes down. We multiply by x to the fourth because the power goes down by 1. If you look at this, you'll see we're doing the opposite of that. If the power increases, it was x to the n, it's x to the n plus 1. Instead of multiplying, we're dividing. But it's very similar, though, so that we could actually check this. Let's just check this once. Let's just check this. If I have x to the n plus 1 over n plus 1 plus c, and I want to take the derivative of that. So let me just rewrite this a little bit. Wouldn't that be like 1 over n plus 1 times x to the n plus 1 plus c? Right? I'm going to take the derivative of this. If I take the derivative, so you guys okay with this? This is the same, right? I just pulled this out in front to make it easier. So if I take the derivative of this thing right here, this is the power. It's going to come down. And I've got n plus 1 times 1 over n plus 1. That cancels. Then you have x to the n plus 1 minus 1, which is just n. So it's just plain old x to the n. The derivative of c is just 0. So it does work. So with that in mind, let's try our first problem with our new power rule. So we've got example problem here. So our function f of x is equal to 4 plus x squared minus 5x cubed, and we want to find capital F. So remember, this is the notation our book is going to use. So it means that here's our function, here's the antiderivative of the function. So what you should do is press pause and try it out, and then check back and see if we agree. So to do this problem, we can think of this. There's a couple ways you can do the 4. To handle the 4, just think of what function has a derivative that's 4. And if you think about that a little bit, you'll say, oh, it's just 4x. Right? Because I know when we get the answer, then this will be our antiderivative. Let me just make a note of that again. This is our antiderivative. We can always check when we get an antiderivative by taking the derivative of it and seeing if we get back to the function. So to get from the 4 to the 4x, just think, what function has a derivative that's equal to 4? 4x. Or you can use this power rule. If you think of this being 4x to the 0 power, then this says go up by 1, so now I'm x to the 1 power, and divide by 1, which doesn't change the 4. So you can get here too. But it's easier just to think, okay, what function has a derivative that's 4? 4x. Then here I'm going to use a power rule. So I'm going to go plus x to the 3 divided by 3, right? I go x to the n plus 1 divided by n plus 1. Right, and then minus 5. And then the power rule here. Just like when you take the derivative, the 5 goes along for the ride. When you take the antiderivative, the 5 goes along for the ride. It's just a constant, it goes along for the ride. So then x, this goes up by 1 to 4, and I divide by 4. So you have times x to the 4 over 4. And then we have to put the plus c. Remember, because there's an infinite number of antiderivatives here, an infinite number, and they're all very similar. They're just basically the same function shifted vertically on the xy plane, right? By adding or subtracting a constant number. So to clean this up, we would say, okay, this is equal to 4x. Probably most of you would write it like this. Plus c. And if you wanted to check, so here's our answer. We're saying this is the general form of the antiderivative of this. This represents every single antiderivative, all the infinite amounts of them, because they're all really similar. The only difference is this c could be any constant at all. So to check, we just take the derivative. So here, let me just say, just to check. If I wanted to check this, I would say 4x plus 1/3 x cubed minus 5/4 x to the 4th plus c. Take the derivative. That would be 4 plus. Now I'm doing the usual power rule. The 3 comes down. 3 times 1/3 is just 1. X squared. You get plus x squared minus 5x cubed. Right, again, the power rule, the 4 comes down, it cancels with that 4, and you just have the 5 left. And it's a negative, that drops down by 1. And I take the derivative of a constant, it's just 0. So we look back at what we had, and that's what we've got. So it works. So this is the antiderivative. So we still have to consider this case here when n is not equal, or when n is equal to -1. So look at this. Think if n were equal to -1, this would be x to the -1, which is 1 over x, right? So if n does equal to 1, or if n does equal -1, then we would get this. We would say f prime of x equals 1 over x, right? Just convince yourself a second. If n is -1, that's a -1. X to the -1 is 1 over x to the +1. And then what we say is f of x, in other words, the antiderivative of that is natural log of x. But we have to be a little careful because there's domain issues here. The domain of this is anything but 0, right? The domain of this, anything but 0 goes. But here, the input to the natural log function has to be positive. So 0 doesn't work, but also none of the negatives work. So the way we do this is this. So this is true. It's natural log of x, but on this interval from 0 to infinity. So what we do is this. We say that the antiderivative of 1 over x, we basically say this. If f prime of x is 1 over x, then f of x equals natural log absolute value of x plus c. So this is what you'll see in any kind of like table of derivative or antiderivatives, or table of integrals as they're called. You'll see that the antiderivative of 1 over x is a natural log of absolute value of x. And we need that just to take care of the domain issues right here. So you'll always see this expressed as a natural log of the absolute value of x plus c, because it only works in these cases. It's not, we have to make sure that this is going to be a positive number. So that's why you'll always see the absolute value there. Okay, so there is the power rule and the special case when n equals -1, which we'll see a lot because we're going to have antiderivatives of 1 over x quite a bit. And then we're going to see a bunch of them that you already know. So I'm going to write some of these down here that you already know. And so we'll say, okay, so f of x equals. So this is where normally if we were in class, I would write a bunch of these down. And you guys would come up, be so excited to get to the whiteboard and write down your answer. This also reminds me of the time when I was in college and I took a Spanish class. And any of you guys who have tried to learn a second language, some of you probably even have learned second, third, maybe even a fourth language. Well, you know that it's not all that easy to learn another language. So in the Spanish class, the teacher was trying to encourage us, and she would say things like, well, you already know quite a bit of Spanish. And I'm like, oh, I don't really know that much. And she'd say, how do you say hello in Spanish? I'd say, hola. How do you say one? Uno. How do you say two? Dos. How do you say goodbye? Adios. She's like, see, you already know quite a bit of Spanish. I'm like, well, maybe I do know Spanish. Well, that's where we're at right here. Okay, I'm going to show you some that you already know. But I'm not going to go so far as to say you can skip Calc 2. But I will say you know quite a few of these just from what we've learned in Calc 1. So f prime of x equals sine of x. It means that f of x equals. I'm going to put a little star here because these two tend to trip us up a little at first. And these two, meaning this is the second one. Okay, so we've got some derivatives here, and we're looking for the function that has these as derivatives. So the first one is real easy. If f prime of x is e to the x, f of x is e to the x. And what do you always want to put? Never forget, plus c. Some of you will be in a Calc 2 class where this plus c carries a lot of points from what I've heard about some tests that can go wrong. So make sure you put the plus c on there. This one we already know, right? Because we know the derivatives of the trig functions. This is the derivative of tangent. So f of x would be tangent of x plus c. And again, you should hopefully be doing these on your own and then checking. And then hopefully you'll get these answers. Now this is one that's a little tricky. We know that the derivative of sine is cosine. But this, and the derivative of cosine is negative sine. This derivative is just positive sine. So the antiderivative of sine is going to be negative cosine. So it's kind of like the opposite. And likewise, the antiderivative of cosine is positive sine. Right? Because just check to go backward. If this is the derivative, if this is the function, f of x is sine of x plus c, f prime of x is cosine of x. So if f of x is negative cosine, then f prime of x will be positive sine. So the signs sometimes can throw us off on these two because they're the opposite of what they were when we took the derivative. Now we're taking the antiderivative. So let's try some of these. This is what we've got so far. Mainly what we're going to be using is the power rule. We're going to use the power rule a lot, just like we did with derivatives. We use it a lot with antiderivatives. And then there's a couple problems that we can do that have to do with dropping a ball. There'll be pretty much physics problems that you'd see when you study the kinematic equations in physics. Now we can do them without the kinematic equations. We can just use calculus. But first, let's get there by doing some warm-up problems out of the book. Like, let's see, this is section 4.9, number 4. It's on page 355. And it says f of x equals 6x to the 5th minus 8x to the 4th minus 9x squared. So go ahead, press pause, give it a try. Okay, so for this one, if this is f of x, then what they're going to want us to do is find the antiderivative. So they would say capital F of x equals. So got the power rule here. So remember, it's the antiderivative power rule. This goes up by 1, and then we divide by that. So here's what we'll have. This 6 goes along for the ride. So 6 here becomes 6 here. And then I have x to the 6th divided by 6 minus 8, x to the 5th divided by 5 minus 9, x cubed divided by 3 plus c. And of course, you guys would never leave a problem looking like this, right? Because these, we can see some things that can definitely cancel here. The 6's totally cancel. 3 goes in here once, goes in here 3 times. So we would get x to the 6th minus 8/5 x to the 5th minus 3x cubed plus c. And let me show you one other thing they'll do sometimes. They'll ask the question this way. They'll say f prime of x equals 6x to the 5th minus 8x to the 4th minus 9x squared. Then they'll say, what's f of x? You guys see this is exactly the same question, just different notation. Here they're saying, here's our function. What's the antiderivative? And we take the antiderivative. Here they're saying, here's the derivative. What's the actual function? We still take the antiderivative. So these are the same questions, right? And these are the two ways you'll see this section of the book ask us these questions in these two forms. Here's a derivative, or here's a function. What's the antiderivative? And here's a derivative of a function. What's the function? But really, they're the same question. And the nice thing about these, you can always check them. So if I get this answer and I'm not sure if it's right, just take the derivative. When you take the derivative, we should get back here. And if we don't, that means something went wrong. Right, so if you take the derivative here, use the derivative power rule, and we should get right back here. Okay, so that is number 4. And another one I've got here is number 12. So let's move this one up a second. Number 12 says f of x equals the cubed root of x squared plus x times the square root of x. So since we have the power rule, we're going to have to rewrite this, right? We have to rewrite it. So doesn't this one really say x squared to the 1/3, right? Isn't it true the cubed root of 8 is 2, and also 8 to the 1/3 is also 2? This is two ways of saying the same thing. This way uses radicals, this uses rational exponents, right? Or fractional powers, they say the same. So you want to do that with these because we need them to be rational exponents. This is x times x to the 1/2, right? And really, even though it's not there, this is understood to be x to the 1. And then we have our rules of exponents that we learned in algebra. Here we multiply. Here we add, right? We multiply in this case, there's x squared raised to the 1/3 power. Here we actually add the powers. It's a different case. There's 2 bases here, just 1 here. So this gives us x to the 2/3 plus x to the 3/2, right? So really this is our function. Just rewritten it with fractional powers, right? Or rational exponents. So then if we want to find the antiderivative, big F of x, here we go up by 1, 2/3 plus 3/3, right? That's the easiest way to think of it. 2/3 plus 1 is like 2/3 plus 3/3, which is 5/3. So I'm going to go x to the 5/3 and then divide by 5/3 plus, here I've got x to the 3/2 plus 1, which is like x to the 3/2 plus 2/2, which is x to the 5/2 divided by 5/2, and then always plus c. Don't forget the plus c. So I know you guys don't even like looking at this problem. Some of you have probably already changed it. So the way we change this, actually this step here, after you do a couple of these, you won't even ever write it like this. Because you think of it like x to the 5/3 divided by 5/3. Isn't dividing by a fraction the same as multiplying by the reciprocal? So to get rid of this fraction inside of a fraction, we could just say this is just 3/5 x to the 5/3 plus 2/5 x to the 5/2 plus c, which is much nicer to look at. So instead of dividing by a fraction, we multiply by the reciprocal, right? Instead of dividing, remember the fraction bar means divide. Instead of dividing by a fraction, we multiply by the reciprocal. So normally I won't use this step. I'll go right from here to here because I'll think of it like this. X to the 2/3 plus 3/3 is x to the 5/3. But I'm not going to divide by 5/3. I'm going to multiply by the reciprocal 3/5. And same thing here. So that's kind of cool. So we want our answer to look like this, right? We definitely don't want to stop at this stage here. Okay, so there's our antiderivative. And then these get better and better. Remember, at this point, we're a little bit limited. We have a handful of antiderivatives we know. Mainly, we're going to be using the power rule a bunch of times. And then they're going to ask us things like 26, where 26 says f double prime of x equals x to the 6th minus 4x to the 4th plus x plus 1. So they want us to find f of x. So it says find f, right? That's what they mean, find f of x. We've got the second derivative, so we're going to have to take the antiderivative to get to f prime. So if this is f double prime, well then f prime is going to be, well, basically I have the power rule a bunch of times, right? So we're taking the antiderivative, so it's going to go up by 1, and I divide by 1. So I have x to the 7th divided by 7, or in other words, 1/7 x to the 7th, right? And then I'm going to just put the -4 here. I'm looking at this one. X to the 4th, the power rule says x to the 5th divided by 5, or in other words, 1/5 x to the 5th, right? And then this is x to the 1, so I'm going to go up by 1, x to the 2 divided by 2, or in other words, 1/2 x squared. And then I have to think, what do I put here so I get a derivative of this thing that's 1? That's just going to be x, right? X prime is 1. And then don't forget, what do we need? Plus c. So I'm going to clean this one up a little bit and get this. Basically, I'm just cleaning up this part right here. The rest of it we sort of cleaned up as we went. So this is f prime of x, but they want just f. So I need to find the antiderivative of this. Now remember, if you're not sure about something, you can always check by taking the derivative of this and seeing if we get back here, right? Power rule for the derivative is 7 comes down, gets canceled there, so it's just 1 x to the 6th. You could go all the way back through to make sure you're going here. So we need to go one more step, one more set of antiderivatives to get to f of x. So to do that, we go power rule again. So the 1/7 goes along for the ride, but this becomes x to the 8th divided by 8, or 1/8 x to the 8th. So I've got the 1/7, and then I've got 1/8 x to the 8th. Oh my gosh, did you guys notice something? This is missing in x to the 5th. See, if we were in the classroom, you could have said, Kurt. But you can't say it now. So, oh my gosh, I'm going to be careful. I don't have anybody to help me when I forget things. Okay, so we get, for this one, the 4/5 is going to go along for the ride. So I'm just going to put the -4/5 here. And then Antiderivative becomes x to the 6th divided by 6, or in other words, 1/6 x to the 6th. Then we have a 1/2 here, of course. And then with the x squared, it becomes x cubed over 3, or 1/3 x cubed. Then we have this x, which becomes, it's x to the 1 right now, right? X to the 1, so it becomes x to the 2 over 2, or 1/2 x squared. And now what about this? What if this said 5? If this said 5, wouldn't you say 5x? So since it says c, it's just some unknown constant, we just say cx. And then we can clean this up to get f of x. So with fractions, of course, we multiply straight across. 1 times 1 is 1. 7 times 8 is 56. Let's get 1 over 56 x to the 5th minus, well, here we're going to get 4 over 30. But what many of you guys would have learned to do is realize that 2 goes in there twice, goes in there 3 times. So we really get 2/15 x to the 6th plus 1/6 x cubed plus 1/2 x squared plus cx. And then we need, we're taking an antiderivative here, right? We're taking the antiderivative of this, so we need another constant. So typically what we do is you just go plus d. Now sometimes you'll see people will use they'll use subscripts. So they'll change this to c sub 1 and then call this c sub 2. But most people just keep going down the alphabet. So when you need another constant here, we just call it d. All right, so we've got another kind of thing. There's a lot of little things that can happen in this section. I want to make sure that you are ready for them. Most of them are not too tricky, but they're just things that we need to be aware of. So 32 gives us a derivative of a function. It says f prime of x is equal to 5x to the 4th minus 3x squared plus 4. But it also tells us that f of -1 is 2. So this is information that we haven't really seen before. It's telling us that when we get to this original function, this f of x, if we plug in -1 in, we're going to get 2. And that's going to allow us to figure out what the constant is. So to see how this works, let's just go ahead and find f of x. So we take the antiderivative with the power rule. This 5 goes along for the ride. This becomes x to the 5th over 5, or 1/5 x to the 5th. Got minus 3. And then the x squared becomes 1/3 x cubed. And then the antiderivative of 4 is 4x, right? Because the derivative of 4x is 4. Then we have our plus c. So to clean this up, you're going to see that these cancel. So we get cx to the 5th minus x cubed plus 4x plus c. But we have more information. We know that when we plug a -1 in for x, the function should be 2. That's going to allow us to figure out what c is. So if I let the independent variable x be -1, so I plug a -1 here, here, and here, this function, f of x, is 2. So using this, we can write this. 2 equals -1 to the 5th minus -1 cubed plus 4 times -1 plus c. Okay, so in other words, we've got 2 equals -1, right? Negative to the odd power is a -1. Now this is going to be a -1, but then we got minus 1, right? Minus 1. Now, just so I'm not skipping anything, let me just write the whole thing down. Right, so we get this minus is right here, right? That minus is right there. And this -1 is -1 cubed. So as you guys know, you have shown me that when you have this minus minus, you make this giant plus like that. So this gives us 2 equals, well, -1 plus 1, that's just going to go. So you get -4 plus c. Add 4 to each side, we get 6 equals c. So that allows us to update our answer. We can do better than this answer. We can say f of x equals x to the 5th minus x cubed plus 4x plus 6. Here is our better answer. And it's just this other piece of information right here allowed us to figure out what the constant was. So we end up with this as our answer. Okay, now I can almost hear, it's like, I know you guys so well, I can almost hear people saying, damn it, Kurt, are we going to do any trig today? Ever? Okay, yes we are. Okay, I can almost hear it. So let's try a little bit of trig, like maybe number 62. You guys are going to be so excited. It says a particle is moving with the given data. Find the position of the particle. With 62, they give us the acceleration of the particle. 3 cosine t minus 2 sine of t. They give us our initial position is 0, and our initial velocity is 4. And they want us to find the position of the particle. Okay, so here's something we need to review a little bit. So if you guys remember, what we've done before is we started with this position function, which is a function of time. We differentiated with respect to t, and we would get the velocity, which was s prime, right? Was the derivative of the position function, or f prime of t, if you want to think of it that way. Then we take the derivative of velocity with respect to t, and we get acceleration, which is velocity prime or position function double prime. So we did this for most of Calc 1 so far. We'd start with the position, take the derivative to get the velocity, take the derivative to get to acceleration. Well, now we're going the other way. So now we're going to start with acceleration, and we're going to take the antiderivative to get to velocity. It's a little trickier because we're going to have a plus c to deal with all the time. And then from there we take the antiderivative again to get back to position. And again, we're going to have to do with a plus c. So it's a little tricky, but it's the same idea. Instead of going this direction, now we're going in this direction. Okay? So with this problem that we're working on, number 62, if you look, they gave us the acceleration. So we are right here. We need to go back here. Okay, so now let's see if I can erase all that mess. Oh boy. Well, look at that. So much easier than a real whiteboard. Okay. All right, so to try this one, we need to take the antiderivative. Oops, I don't want that. I want this. So to get from acceleration, we first go to velocity. So just think, what function do I put here whose derivative is cosine of t, 3 cosine of t? Well, that's going to be 3 sine of t, right? Because the derivative of 3 sine of t is 3 cosine of t. And now I need something right here whose derivative is -2 sine of t. I'm going to make a mistake here. Let's see if you guys can catch it. I made a mistake. Because the derivative of cosine is negative sine. So if we want the negative to be here, we need to make a positive here. Next, we need a plus here. And then we have plus c. Well, we can find the c because they did tell us this, right? They tell us that when time is 0, independent variable t is 0, the velocity is 4. So let's see if we can figure that out. Let's use that and see if we can find c. So I'll do this one in red. So 4 equals 3 times the sine of 0 plus 2 times the cosine of 0 plus c. Well, sine of 0 is 0. Cosine of 0 is 1 though, right? Cosine of 0 is 1. So we get 4 equals 2 plus c, right? Because this is 2 times 1. So if you subtract 2 from each side, you will get 2 equals c. So now we can update this velocity formula. We can update it and say, okay, the velocity is equal to 3 sine of t plus 2 cosine of t plus 2. So there's the velocity. Now we want to find the position function. So we take the antiderivative again to get s of t. And remember, typically when you have position, velocity, or acceleration, the independent variable is usually t. It doesn't have to be, but a lot of times t is used because usually with these functions, our independent variable is time. So the antiderivative here, we would need a function whose derivative is 3 sine. Well, I can't put 3 cosine because the derivative of cosine is negative, so I need to put negative 3 cosine of t, right? Because the derivative of cosine is negative sine, so I need the negative here, so the derivative of negative cosine would be positive sine. So that's the part that is really easy to get tripped up with these trig functions when you take the antiderivative because we're used to the signs being the other way. So taking the antiderivative is a little bit like if you're right-handed, it's going to seem a little bit like you're throwing left-handed. And vice versa. If you're a lefty and you're throwing right-handed, it just seems a little awkward because you're doing everything backward. And it will seem like that for a while. So the derivative of 2 sine of t is 2 cosine of t. And then we need the antiderivative of 2, which is 2t. And now we have another constant. I'm just going to use d just because, I mean, you can use really anything, but it makes it, if I use a c, it looks like it should be the same as this c. So I'm just going to use something else. And then we're going to use the other piece of information, which may be too far up for you to see it, but this is the other piece of information they gave us. They said that when time was 0, position was 0. So if we plug a 0 in for t, the position is also 0. So I'll use this in red again. I'll say 0 equals negative 3 times the cosine of 0 plus 2 sine of 0 plus 2 times 0 plus d. Well, these two are just going to be 0, but cosine of 0 is 1, so you get 0 equals negative 3 plus d. Add 3 to each side, you get 3 equals d, so that our final answer for our position function is negative 3 cosine of t plus 2 sine of t plus 2d plus 3. So this is our position function. Okay, and this brings us to our last problem, which is probably the most interesting and the most important problem. This is the kind of problem that you'll see a lot because it's an applied problem. This is number 65. And this one is on page 357. This problem will be our last one, but it takes a little while to do this problem. So make sure you're with me on this one. This problem says a stone is dropped from the upper observation deck of the CN tower 450 meters above the ground. And then it's going to ask us a whole bunch of questions. These are the kind of questions you'll see in a typical physics class. A lot of times with a trig-based physics class, if you don't learn calculus, you'll do these kinematic equations, which are actually a lot harder to do. If you know calculus, it's a lot easier to do these kind of problems. So with this one, it says find the distance of the stone above the ground level at time t. Well, for these, all we really need to know to get started is the acceleration due to gravity. So acceleration at this height, 450 meters and below, acceleration for all practical purposes is going to be constant. So for pretty much for any kind of dropped ball problems, we just assume acceleration is constant, and it will depend on what unit of measure you're using. So what we're going to use is negative 9.8 meters per second squared. Sometimes people put another significant figure here and they say negative 9.81, but we're just going to use negative 9.8. And if we're using the English system, we'll use acceleration equals negative 32.2 feet per second squared. This is acceleration due to gravity, and this is all we need to get started with these kind of problems. So for our problem, we're talking about 450 meters above ground. So for our problem, we're going to use this. If they had said something about some measurement in terms of feet, then we'd use this other one. But these are going to be held constant. So into to these, to the nearest 10, it would definitely be constant for any kind of problem like this. So we'll just assume these are constant acceleration. And so we already have the acceleration. So we've seen if we have acceleration, we can get to position, right? So it seems like they don't give us much. They just say, oh, it's 450 meters above the ground. And they start asking us all kinds of questions. But we do know acceleration due to gravity. This is the acceleration due to gravity if you use a metric system, and this is using the English system. So a couple of things to notice here. It's got a negative sign. So we're going to use, it's kind of a traditional thinking of up as positive and down as negative. We can think of acceleration as gravity pulling the object down. We can think of it like that. And that acceleration is going to increase by 9.8 meters per second squared. And it's a negative, which means it's going down. And here, it's just going to be feet, of course, per second squared. And remember the notation here. When it says meters per second squared, that's really meters per second, right? And I think I showed in class, meters per second squared is how you write it, just because it's so awkward to write it in this other way. But this really means meters per second divided by second, which is like meters per second times 1 over second, and that's where you get that meters per second squared. So it makes sense to think of it like this. It's a change in meters per second, which is velocity per second, right? That's acceleration, change in velocity, but it's so awkward to write it like this that we typically just write it this way. So, okay, let's get started with this one. And actually, I should mention one thing too. I'd mentioned that some of these problems you'll see in a physics class where you use kinematic equations. You might think, well, why don't we just always use algebra? Well, there's times when you can't use it. So kinematic equations don't work for acceleration that's not constant, and there you would actually need calculus. So although they can work for some problems, they're usually more work. It's usually much easier using calculus. And then there are problems where they just won't work. So getting started with this one, we've got our acceleration function. Let's come up with the velocity function. And I'm gonna write this just to emphasize. This is acceleration at time t. It's negative 9.8. That's a constant. There's no variable here. This doesn't change at different values for t. It's always negative 9.8. It's constant acceleration due to gravity. So then, to find the velocity, I need to take the antiderivative of acceleration, and that is going to be negative 9.8 t plus c. So to figure this out, we have to think about what we're doing with this problem. So it says that a stone is dropped. So since the stone is dropped, we need to know something about that word. Dropped means the velocity initially is 0, right? If it said thrown down means the velocity is negative. So if it said thrown down at 5 meters per second, we'd say velocity initial equals -5. If it said thrown up, that means velocity initially is positive. If it said thrown up, straight up at 10 meters per second, we would say velocity initial equals 10 positive. But when it's dropped, it's like you're holding a stone, and the instant you let it go, you're not throwing it, you're just dropping it. For that brief moment in time, the velocity is 0 meters per second. So we can use this. We know the velocity at time 0 is 0. So if I use that in red here, when time is 0, velocity is 0. Which basically means that c equals 0. So when it's something like this, you can kind of see what's going to happen. This is just going to be a 0. So you just get here. Some of you guys you may have recognized from kinematic equations, you'd see this -9.8t plus v naught for the initial velocity. So, but anyway, we can update this. So we've got, let me circle the ones in blue that are the formulas we're sticking with. There's acceleration. And now velocity, we can improve that. We can say our velocity formula is -9.8t. There's no constant. The constant is 0. That's because our initial velocity is 0. So we've got acceleration, we've got velocity. Because once we get these three functions put together, then we can answer any question they ask us. So we need one more. We need to find position. So to find position, let's take the antiderivative of this. And what we'll have to do, this will go up by 1 to 2, then we divide by 2, which means we're basically going to divide this by 2. And you'll see -4.9t squared plus d. And again, if you have taken those physics classes, you'll recognize this also. -4.9t squared. And then if this were the general case, we would actually have v naught times t, right? For this would be v naught. But we just have this. So this is our position function. And now it does say that it was dropped from a point 450 meters above ground. So we can use that. They basically initially told us that position at time 0 is 450, right? Because it was dropped from this deck 450 meters above the ground. So our position at time 0, our initial position was 450 meters. So we can use that here for position when t is 0, the position is 450. So you could say, okay, 450 equals -4.9 times 0 squared plus d, which means that d is 450. So now we can improve our position function. We can say position function is -4.9 t squared plus 450. And now we've got, for this situation, when we're dropping this stone, and we're ignoring air resistance in this case, so I may have not mentioned that. In these drop ball problems, we will ignore air resistance, but it's like everything else. When we first see this problem, we think of this simple case. And then when you are in either differential equations or maybe physics, you'll add in one more term to handle the air resistance. And in a lot of cases, something like this, if the stone is heavy enough, and like if it's like a ball bearing kind of thing being dropped, a lot of times air resistance won't change it a whole lot. But air resistance is something we'd always have to consider. But first we'll learn this, and then we'll make it a little more realistic by adding to it. But you can't handle the most realistic case the very first time you learn something. So we'll add in pieces as we go. But this is the bulk of it. If you understand what we're doing right here, as you get done with this and you're real solid on these, adding air resistance is going to be easy. So just keep in mind for this one, we're going to completely ignore air resistance, and we will ignore it in Calc 1. So we've got these three functions now, and now we can answer any questions they want. So part A, it says, find the distance of the stone above ground level at time t. We just found it, actually. This right here, this is actually part A. This will give us the distance above ground at any time t. So when t is 0, plug in a 0 for t, you get position 450, which makes sense, right? Initially, we're 450 meters above ground. So plug in any time that you want for t, and it'll give you the position function within reason, right? Because this is a mathematical model, and a good mathematical model will work on a window, but it doesn't work forever. So if I plug in 100 in here, I'm going to get a huge negative number. It doesn't mean this stone is burrowing into the earth, right? It just means that this model is going to end when the stone hits the ground, right? Then it will not meet anything anymore. So that's part A. Part B says, how long does it take the stone to reach the ground? Well, when it reaches the ground, the position will be 0, right? So we've got position will be 0, and so we can solve that. So for part B, we just need to solve this. So part B will say 0 equals negative 4.9 t squared plus 450. So this is part B. Because when it reaches the ground, so think of there's this cliff. I know this isn't exactly the case, but we've got this stone that's 450 meters up, right? 450 meters. And they drop it, and it starts to fall, and it hits the ground. So when it's on the ground, then it's at 0 meters, so position is 0. So we basically just have to solve this, right? So let's do a little algebra here. 4.9 t squared equals 450, which means that t equals the square root of 450 divided by 4.9. So t equals, remember significant digits, you guys are going to learn about that in another class. So we'll just say 9.58 seconds. And so that's how long it will take to reach the ground. With what velocity does it strike the ground? Well, if we know how long it takes, then we can definitely figure out the velocity because we got a velocity formula right here. So we just take this 9.58, plug it in right here, right? So this is part C. With what velocity does it strike the ground? Here's part C. Velocity at 9.58 equals negative 9.8 times 9.58, right? Because I'm just plugging that time into for the velocity formula. And we get roughly, we'll say negative 93.9. Now, a couple of things. Let's make sure we always put the units on these. This is velocity. It's meters per second, right? Velocity, change in position over change in time. Position is in meters, time is in seconds, so velocity is meters per second. And what's the significance of the negative? Remember, the negative means it's going down, right? So the velocity is negative 93.9 meters per second. It's going down at 93.9 meters per second. Remember the shortcut. If you have meters per second and you want miles per hour, you just multiply it by the square root of 5. It's just a real easy one to remember, and it typically will be accurate to about 2 decimal places or so. Instead of going through the whole, unit conversions, you can just multiply meters per second times square root of 5 to get miles per hour. It works pretty well. And speaking of that, there is one of the homework problems where they are going to ask us about, they'll give it, I think they give it to you in feet per second, and you need miles per hour. So let's just quickly practice one of these. Before we do part D, let me do a quick practice problem. If you have 30 miles per hour, and you want to know how many feet per second is that? This is just a review from algebra class. 30 miles per hour. We use these unit conversions, right? And we want feet per second. So I need to change miles into feet. So multiply by 1, right? 1 mile is 5,280 feet. Right, isn't our system nice? Random numbers. So 1 mile is the same as 5,280 feet. So we're really multiplying by 1, but it allows us to cancel miles, right? And then we're left with feet, which is what we want. Then we need to get hours into seconds. So we multiply by 1 again. I'm going to put the hours up here because I want them to cancel with this hour down here, right? So I want hours to cancel. And 1 hour is 60 times 60 seconds, right? Or 3,600 seconds. Or you could do two conversions, hours to minutes and then minutes to seconds. But either way you go, hours will cancel, and we're left with feet per second. And then you just multiply straight across. It's just fractions. 30 times 5,280 times 1. This would be like 1 times 1 over 3,600. So we end up with 30 times 5,280, and we divide that by 3,600, and you get about 44 feet per second. So it's just a quick review. So if you have to use unit conversions, that's how you do it. Okay, this is a long video. I hope it uploads okay, but we need to do one more part for part D. And this makes it a little more challenging algebraically. But part D says, if the stone is thrown downward with a speed of 5 meters per second, how long does it take to reach the ground? So now we've got, this is velocity initially is -5, right? Meters per second. So let's think of what else we have. We know that initially the position is 450 meters. And we can use, let's see, we can use the acceleration. That's not going to change. It's -9.8, right? So this stays the same. Acceleration is -9.8 meters per second. Now when we find the velocity, though, we're going to get -9.8 t plus c. But now we have to make use of this, right? This says when time is 0, velocity is -5. So now we're going to put -5 equals -9.8 t, and actually not t. T is going to be 0. So you get -9.8 times 0 plus c. So we end up with -5 equals c. So our velocity now is going to be -9.8 t minus 5, right? Because we're improving on this one. Before c was 0, now it's -5. So now our velocity formula looks like this. So it's got another term from what we had before. So if we want to, for part D, it says how long does it take to reach the ground? Well, we need a position function again. So we need to now find position function, which is going to be, I remember the t goes up by 1, and then we divide it. So we get -4.9 t squared minus 5t plus d. So now we're going to have to use this piece of information. So this says that when time is 0, the position is 450. So we get 450 equals -4.9 times 0 squared minus 5 times 0 plus d. So 450 equals d. So now we can improve on our position function. We can say s of t equals -4.9 t squared minus 5d plus 450. So here is our new improved position formula. So part D says, how long does it take to reach the ground? Well, it will reach the ground when this position is 0, right? When this is 0. So we just have to solve. We set this equal to 0 and solve. So to answer the question, we basically have negative 4.9t squared minus 5t plus 450 equals 0. So this is more work than the other problem because we have this term here. So we are going to need the quadratic formula, or you might be saying, how about Newton's method? Newton's method would work. For Newton's method, let's plug this into y1, right, in your calculator. Take the derivative of this, which would be negative 9.8t minus 5. Put that in for y2, and you could walk through Newton's method and solve it that way. You probably, if you don't, you should have a quadratic formula program in your calculator, because it's just nice to have that in there. Otherwise, if you do it by hand, x is equal to negative b plus or minus b squared minus 4ac all over 2a. Of course, you could also graph this on the calculator and see where it crosses the x-axis. Either way you go, it looks like you will get 2 answers. And one of them makes no sense at all. Right, this is negative. We don't have negative time. So the only answer that makes sense is this one. So 9.09 seconds is what it takes. So it's a little faster, because what was it last time? Last time it was like 9.58 seconds. So it's a little faster if you throw it straight down. So give those problems a shot. Some of them are a little challenging, so give them a try. And if you have any questions, let me know.